Hello, everyone. Thank you for attending this talk. My name is Zach Probst. I'm a senior software engineer at Intuit, and I work on the platform security and compliance group at Intuit. And the title of this presentation is Security and Velocity through Declarative Ingestion. And my hope is that by the end of this talk, you will know what all those words mean in relation to one another and how we at Intuit have been able to do some cool security work with graph databases and consuming lots of data with it. A little bit about me, just before we get started. I'm originally from Hershey, Pennsylvania, and a side effect of growing up in the backyard of one of the largest independent amusement parks is you become a roller coaster aficionado very quickly. And I didn't stay in Hershey forever. I went to school in Rochester, New York at RIT. If you've never been to Rochester, you'll know it's a very cold and a bit desolate place, but it's also very beautiful in the summertime. So if you're ever going to visit Rochester for something, I hope it's in the summertime. I've been an engineer for a while now. I cut my teeth in Ruby and C#, and I kind of drifted into Python after that. Recently, I've been really loving writing Rust code. As a security guy, it provides a lot of benefits in memory safety and other things to write secure software. But let's talk about not about me. So we're going to go ahead and skip to our work at Intuit. I work on an application which is starting to become known as the Security Knowledge and Insights Platform. Prior to this, we used to call it the Endpoint Mapping Service. And the name change is representative of the kind of success we've had with aggregating together data in a graph and using that to secure Intuit. And in particular, our mission statement is securing Intuit through visibility, hygiene, and collaboration. And so we try to gather a bunch of data sources from across the company and kind of make sense of it to solve security problems. So to kind of journal our story, in the beginning, Intuit didn't have a great way of attributing software to sort of host names, DNS endpoints out on the internet. It's hard to see behind abstraction layers and content delivery networks and all kinds of other things like that. And there isn't a great way other than to manually kind of trace your way through all the applications of Intuit and understand how they interrelate. Applications at Intuit are built from lots of microservices and micro front ends, and so understanding the composition of any endpoint and where a particular security vulnerability may lie is quite difficult. Fast forward to today, and we have a graph that's over 7 million nodes in size, roughly 45 million relationships. And to build that, we process data from over 20 data sources and process hundreds of millions of records per day to distill all this information down. What we're able to do is sort of provide ownership of who owns a particular endpoint or a particular URL on the internet in like 100 milliseconds. And we can tell you all kinds of information about it, like what GitHub repos is the source code for that application, who's the dev manager responsible for it, where it's deployed in our cloud, what technologies compose that, and a whole lot more. And to sort of exemplify that, this is www.intuit.com, the corporate host name of our company. And as you can see, there's all kinds of dots. It's like confetti. There's just a collage of different colors here. And don't try to make sense of what this is. Just try to make sense that there's lots of data coming together from different sources to kind of stitch together a story for every given application in the company. And if you think about your own enterprise or your own company, you rely on lots of vendors, and you kind of compose them together to build your environment, right? You might have source code that's managed on GitHub or GitLab. You might have CI/CD that's something like Jenkins or Circle CI or what have you, and you're deploying it onto a cloud like AWS or Google or Azure. You might have a CDN in front of it like Cloudflare or Akamai. And presumably you also try to secure it. So you might run over your source code and your applications tools like Sneak or Veracode to check for common security vulnerabilities, check for vulnerabilities and third-party dependencies that you may be relying on, and a whole lot more. Even things like Kubernetes and stuff like that. All of this together is what it sort of represents how your application gets built from a developer all the way to production. And understanding the story that every application goes through uh, is complex, and it requires data from all these different places. So you might be asking yourself, like, okay, so what, right? You have a lot of data, you put it in a graph, like, we're done. Turns out that it's not quite that simple. Um, and to get a sense of it, you have to think about like what the first step is. And the first step is to ingest all of this data. And ingesting a lot of data means that you have to like write code to scrape from APIs or access a system and stuff like that. And a lot of the code ends up looking like this, where there's like random like or zero. Like I don't I wrote this code and I don't know why the default version is zero anymore. Right? It's long past. It's been cast off into the void. Or up above that where it's policy info status. If the activation object doesn't have policy info or status, that code's going to break. Um, so all this is it's very easy to write brittle code to kind of tease out the information you need in complex data, and to be able to distill that to nodes and relationships. Once you have that data, the graph database takes care of connecting things in such a way that makes sense and lets you explore it. But getting the data distilled from all kinds of different formats is quite challenging. Even if your organization is itself very disciplined about how it structures data and has strong schemas for things, like I said before, your organization also probably relies on a lot of vendors that may not have that same discipline and schema, or just have a schema that's not very convenient for projecting into nodes and relationships. And so this is a kind of further example of that. Like, there's all kinds of crazy things that can go wrong when you're sort of teasing through data, right? A value you need for a key or a property might be null. What do you do then? It might be drilled deep into like lists of objects that have lists themselves of other objects, and that value is all the way deep down in some crazy complicated JSON structure. Or you might just have crazy things like a JSON string encoded in JSON, right? Like, what are you to do with that, right? So you have to write all this very brittle, complex code just to be able to use a graph database, just to be able to ingest all of this stuff. And so this is the problem we found, is that it's hard to kind of uh, sustainably do this. For a given data source, you can hack together a Python script pretty quickly to gather all this data. But when you start adding tens of data sources to your application, it's tough to be able to do this repeatedly and fast. And to sum it all up, writing code for each one of these data pipelines is a nightmare. It really slows you down and limits your ability to provide value to the organization. And so enter our solution, which we call declarative ingestion. And the idea is that essentially what we're doing is ETL. And there's lots of different ETL frameworks out there that let you do all kinds of stuff. But at the end of the day, you still have to write some code for a lot of these things. And we wanted to really minimize that and provide a way where you can quickly, and sometimes as low as an hour, introduce a whole new data set to the graph. If you think about what an ETL job is, it's here's some source of data, and then you need to transform and filter that data down into the things that you're really trying to get at. And then in the case of ingesting stuff into a graph, you need to be able to turn that thing into a series of nodes and relationships. You kind of need to project it into its own little subgraph. And then once you do that, you have to figure out some way to deploy it and run it, right? It might be a scheduled job that you have to pull data every so often, or it might be something where you're listening on a Kafka topic or a stream of some kind and just ingesting stuff that way. And our goal is to be able to do all these things in such a way that you don't have to drop to code. You don't have to drop to writing infrastructure as code either. Everything's just kind of sleek and easy to do. And that's what I'm going to kind of walk through how I've done that. So the first step is what we call the extractor. This is your source of data. And there's all kinds of, in our framework, we have all kinds of built-in implementation. This one is one that reads from a Kafka topic. There's a layer on top of Kafka called our event bus that does some encryption and a few other things. And you'll see that the first step is that we just basically point it at a topic, give it some credentials to use to read from that topic. And from there, we're able to retrieve records from it and feed it through the rest of the pipeline. Another example of an extractor, you might imagine things like I mentioned before, Kafka. You might write one for SQS or something like RabbitMQ. You might also pull stuff from a data warehouse or a data lake. You can think things like Google's BigQuery or Amazon Athena, Vertica, all that sort of stuff. And we talked a lot about pulling data from APIs from different vendors and things like that. The way we typically do it is we write a scraper for that API and then ship the items across a stream, like the Kafka stream as mentioned before. And I'm going to note a distinction here between sort of infinite extractors and finite extractors. If you run like an Athena or a BigQuery, it's going to produce a finite number of results. So your extractor is going to run out of data at some point, versus a Kafka topic where your extractor is just going to keep pulling and keep waiting for more data. And so you have to kind of run those two workloads differently. If you're deploying something that never terminates and constantly needs to pull, that's something that has to run on sort of like a perpetually running container, right? It can't be a cron job that kicks off every so often. So we kind of needed a way to distinguish these. We'll come back to that in a second. I just want to point out that differentiation while we're talking about extractors. The next thing is to kind of massage the data, right? There's maybe you need to filter out certain data. You need to manipulate data. If you go back to that, like the encoded JSON in a string thing, we have transforms that will take that thing and sort of decode it as JSON and put it back in the object. We have filters that make sure a particular value is one of a list of possibilities and things like that. And as we encounter new use cases, we implement kind of these reusable components, right? If you look the expand JSON fields, the one on the right, you can think, hey, we didn't build like the expand this particular field in this particular object transform. We built a generic transform that can be reused across different pipelines. Same thing with filters. Before we continue, I want to do a quick little aside on JamesPath because it's going to set us up for the next section of this. If you're not familiar with JamesPath, it's basically a query language for JSON. So I have a couple examples on the screen, but in general, what JamesPath lets you do is it lets you drill deeply into complex JSON structures or complex JSON documents, and tease out the exact data you need. And you can even do more complicated things, like you can slice arrays on a particular index, or you can project some part of it as something else, and all kinds of things like that to kind of minimize or narrow down the data that you're looking at to a particular thing. And this is how we get at the necessary fields that we need to draw nodes and relationships out of these complex documents. And we do so with a mechanism that we call interpretations. And the idea behind interpretations is you're looking at a document, and that document tells you a bunch of different things. For instance, it tells you, hey, this thing this field should be used as the primary key of a node, right? So if you're looking at a user and it's got like an email address, maybe that's a unique way to identify a user, right? In this example, we're sort of encoding the org chart of Intuit. And so I created an employee type or a node type called employee. And the key for that is the email address. Because in our system, our email addresses are unique to an individual. So we use that as the key of the node. And then next to it has another field in this object is the manager's email ID. And so we can create a relationship called reports to another employee. And that way we're bootstrapping up an org chart. And we can also do other cool things like extract variables and then use them later in some other place. The way all this works is it kind of gets distilled into an intermediary representation of nodes and relationships. We have sort of an in-memory model of nodes and relationships we're creating per record. And then that in-memory model gets fed to something that upserts this information into Neo4j. And so just for fun, this is the Intuit org chart blown out 5 degrees from our CEO, just to kind of prove that it works. And as you can see, it gets pretty hairy pretty quickly. You might be asking yourself, though, like, how do we test all of this stuff? And we went back to the playbook on this one, and we found that in JavaScript, there's a testing framework called Jest. And one of the technologies it has is something called snapshot testing. And the idea is, like, you give your code some input, and that produces an output. And then it stores that output. And then every time the tests run, it runs it again and ensures that the output matches what it was before. And so we use our in-memory representation of nodes and relationships to act as our snapshot. So we give it a reference to our pipeline file, which is made up of all the components we've talked about so far. And then we give it a sort of test set of data, a test fixture of data. And then we use the snapshot component to make sure that that snapshot matches every time. So you can go in and tweak the pipeline, or you can change the underlying engine. And as long as your snapshot matches, you know that it's going to work. Obviously, we test locally and test in pre-production environments as well, but this is how we sort of write automated testing to ensure that given the same input, the same output is produced. Now the next phase is we've got some data, we've interpreted that data as nodes and relationships, we've tested it locally, we've run the snapshots, we're ready to roll this out, right? So the last part of this puzzle is what we call the registry. And the registry is basically just a list of all these different pipelines. And this is where that distinction comes back between things that are infinite or finite. Things that are finite, we can run on a cron schedule. So we have a block on the bottom right. We have a block for different pipelines and the schedule that they operate on. And for things that are infinite, we can define the same pipeline definition, but we can also give it how concurrent we want that to be. Some of our topics are drinking from a fire hose, and one instance of our pipeline is just not enough to churn through all the data, where others it is. And so what happens is we have Kubernetes workflows that basically read this file and provision the necessary cron jobs or pods running in a replica set to handle the load of all these different pipelines and distribute them. And so we don't have to write a whole bunch of Kubernetes resources ourselves. We have some sort of automation that reads this and then produces those jobs automatically. And it lets us be able to churn through creating all these jobs very quickly. And so here's the end-to-end flow of all of this. The data is on the left, the graph database is on the right, and the story in the middle is what we've been talking about so far. We have some things that come out of like data warehouses and things like that, operational data that we can just read directly in through cron jobs. And then for vendors where we're scraping APIs and pulling data, we have a cacher that pulls that data, sticks it on a Kafka topic that we then ingest. And the declarative ingestion is all the stuff that's in the Munchlax box. Munchlax is the code name for our service that we use to ingest all of this data. And the output, again, of course, is the Neo4j instance. On the other end of that, I talked about our API before. So we have an API that sits in front of the graph database and also expose Bloom for visualization to some of our customers as well. This slide sort of potpourri. It's a couple miscellaneous thoughts about all the way the mechanics of some of this stuff works. So first, we run all of our data off of a TTL. So as things expire, they're removed from the graph database, and we set definitions for different nodes and relationship types and give them each an individual TTL, because some data is collected more frequently than other data, just by the nature of some things change more often, right? For an example, EC2 instances or virtual machines get torn down and stood up all the time, right? It happens very frequently. So we collect that every hour, as opposed to something like um, the contributors to a GitHub repo. That changes fairly infrequently, right? It's usually the same people that contribute to a GitHub repo. So we don't need to collect that as frequently. And so basically everything gets periodically recollected. So if it maintains its presence, right, if that virtual machine sticks around for a long time, or a database or whatever sticks around for a long time, we'll keep seeing it and we won't ever TTL it out. But things that are sort of have drifted off, we eventually TTL out. Some other notes about developer experience: we have the ability to kind of automatically create the necessary constraints and indexes that are used in the ingest. So by nature of you referring to a particular field on a node and saying, hey, that's the key, it'll create an index automatically as it starts to ingest that data or ensure that the index is in place. We also have a whole bunch of links that are in place to make sure that you define TTLs, that your key usage is consistent across different pipelines. So if you have 5 pipelines and 4 of them refer to the employee node by their email, and the last one refers to the employee node by its by the person's name, that's sort of an inconsistency that we try to avoid as much as possible. And the last thing is, I think one of the key points around the way that we do this quickly is that it's composable. We can reuse these sort of building blocks between different pipelines, and then only reach for creating new code when all of the building blocks we have don't solve the problem. And so, we might have to create a new transform or change an existing transform to support manipulating data in some new way. And this allows us to write a lot less code and churn through adding new pipelines to our data, or adding new ingests or pipelines into our graph very quickly. So what has all this bought us? The answer is a lot. So we're able to handle significant amount of load. So we have certain topics that don't even register sometimes. So the charts on here are the backlog of items on a given topic. And so there's just almost never a backlog because of how quickly we ingest some of this stuff. And others that produce hundreds of millions of records, maybe sometimes we'll have a couple million as a backlog, but usually it's pretty close to 0. And so we're able to look through all kinds of data and project it into a graph at kind of an extremely quick rate. And we're also able to do this without just blowing up the database. So one of the critiques we heard when we started using Neo4j was that sometimes it's slow with writes, and it hasn't been our experience. We're able to, for the most part, keep our ingest in sort of the 10% of CPU range on a 32 gigabyte cluster, which is not huge by any stretch. And we're able to keep things as low as like 2 to 3%, depending on how bursty our ingest of data is. But as far as business outcomes, we're able to introduce about 1.5 PRs per working day, which is kind of a lot. And we're about a 3-person team. I say about because there's 2 people that are full-time, and we've had some people kind of contribute stuff here and there on a part-time basis. One of our projects we have is to score the risk of every asset in the company. And we're able to produce 100,000 risk scores in 4 minutes, thanks to all of the data we're able to aggregate and stitch together. That's including all kinds of things like the presence on cloud, right? What your posture is on cloud, if you're configured to talk to third parties, and all kinds of stuff like that. So it's very complex traversals, and we're able to do it extremely quickly. Intuit's also a very big company. It has a huge presence out on the internet. It has a very large attack surface. And we're able to attribute over 500,000 different DNS endpoints or host names to the owners, to the code, to the vulnerabilities that may or may not be associated with any given endpoint. And we're able to do it in milliseconds. And one of the on that note, one of the interesting things about this, because we're able to add new data so quickly, whenever there's a 0 day and there's some new piece of data we need to look at to find out if we're exposed, we're able to turn it around very quickly and do analysis. If you're in the security space, you might be aware of the OpenSSL vulnerability that recently hit. There's a lot of cool things in there that require you to analyze the system, not just the dependencies that belong to the application. You have to know about the system that it's running on, and we're able to ingest some of that data very quickly to analyze it. There are some shameless plugs I want to throw out. My coworker Chad Close just wrote an article about the way we deobfuscate some of our infrastructure at Intuit. On this topic, it goes into some of the detail. There's some code there as well, showing off kind of the proof of concept of a lot of the things we've talked about here. And I would also like to foster a community around this, if at all possible. We're looking to open source a lot of what we talked about here in some capacity. So if what you've seen is valuable to you, if it's something that you might find yourself wanting to use, please reach out to me. My email is right here on the slide. It would be great to kind of generate some interest around this and foster a community around it. So I have some time for Q&A if there's any questions. I've been monitoring the chat. I don't see any questions, but I'll give it a minute to see if anyone has something, brings up a thought. So excited, motivated. Yeah, Aisha, I think reach out. Let's see if we can collaborate in some way. Yeah, that sounds good, Michael. All right. I think I have a few more minutes left. Let's see, Gabe, by asset, you mean all developed software and services? Yes. So asset is a bit of an Intuit term. Basically what it means is any piece of software or service that the company has developed. And so we're able to attribute to services, to websites, and then from there, what the source code is and all that sort of stuff. Michael asks, what was the biggest challenge in building this? I think it's really how to say it, finding the data that actually is proved valuable to add, and sort of building sort of a manual graph, if you will, of all the data. So if you have data set A and B and C and D, and you're trying to figure out how to get that path, right, you kind of have to look at some of the data before it's in graph to see how it kind of pairs up, and then from there turn that knowledge into ingestions. And digging through all the data before it's in graph form is, I think, probably the hardest part. Does the declarative ingestion tool or framework only work with Neo4j? So currently, yes, in that we only have sort of one output to Neo4j, but the framework has the ability to kind of swap in a write component. So you just need to implement the writer for some other database, right? And that would probably require like a change in query language or things like that. So the framework is there for that. The framework was built to support that. We just have never implemented any other source or destination but Neo4j. Great. So I think questions have mostly dried up. So I just want to thank everyone for your time. It was great being here.